wonderful place. I'm really jealous, I have to say, that you can do science in such a beautiful surrounding. As Sylvia mentioned, I mainly work on preimplantation development in mammals, mainly on mouse, but today I will try to tell you a story about rabbits as well, and why do we think that we need to start working on various types of mammals, not only on mouse. It's not like I have anything against mouse, but I think we have to extend our horizon. Okay, why do I work on preimplantation development? Why it is important? So we work on this period of time from fertilization, when the two genomes become connected in one cell, till implantation in maternal tissues. And this is a very special moment of our development. The first three embryonic lineages are established, and I will be talking a little bit about that. And if these lineages fail to be established at this stage, you have either no implantation, or if you do have an implantation, then the embryo will be quickly aborted. And as we know, probably at least 50% of the embryos after natural fertilization will be lost around this stage. I think it's important that we learn a little bit more about our own development. But to do it, we study mouse mainly, and here I will just play for you a little movie about the development of mouse embryos. So we have a 2 cell stage which divides to 4, and then the 8 cell stage. So the embryo first is going through the cleavage stages, where the cells become smaller and smaller and smaller, because there is no growth phase. I will play the movie several times so you can see it. So you see the cleavages. No growth phase, so the cells are getting smaller and smaller, and eventually we stop seeing the difference between the cells with an embryo, and this is because of the compaction of use. So basically, the blastomer, which originally can be easily distinguished, start to adhere to each other due to increase in cell-cell adhesion, and we have this ball of cells which we call morula. And this is the first differentiation event in mammalian development. So you can again observe it here. First, we clearly see each blastomer itself separately, and then we cannot see the difference anymore. And eventually, the embryo will form embryonic cavity, blastocyst cavity, and at this stage, we call it embryo blastocyst. And this is the stage when embryo is ready to implant. As I mentioned to you before, during this period, the first lineages are established. So by the blastocyst stage, we have 3 lineages present. The surrounding embryo, marked here in green, lineage, which is called trophectoderm. This is the first epithelium in mammalian development, and is necessary for implantation, and then form embryonic part of the placenta. We have this blue line here, line marking blue, which is called primitive endoderm, which originally will be feeding the cells, which will make a fetus, and then become a very important signaling center. It will give a signal where is the head and where is the tail of the embryo or fetus. And then we have this most inner cell group of cells, which is here marked in red, which is a pluripotent cell line called epiblast, and epiblast will form almost all of the cells in our body. So, what is interesting, although we know by now quite a lot how the Drosophila develops, how Xenopus develops, we still don't know how this red line is specialized in mammalian development, which is a bit embarrassing, but that's where we are. But we know a little bit about it. So what do we know? We know that originally each blastomer, so basically each cell, embryonic cell, can contribute to all of the lineages, extra embryonic lineages like placenta, or embryonic lineages like the ones which will form fetus. And we call the state totipotency, so it means they can do everything. But then the embryonic cells undergo 2 binary sulfate traces. So during the first one, we have a specification of a group of cells which become the trophectoderm, and specification of the most inner group of cells, which will form inner cell mass. So how does it start? So as I mentioned to you before, at some point, the blastomers start to adhere to each other a lot, and at the same time they develop polarity. So you have an apical surface facing outside, which start to have a certain protein localized, and basolateral. Very well, but basolateral, maybe I will show you using the mouse. Basically here. Yeah. Now, when the cells divide to the next stage, they can either divide in the way that both cells inherit this apical domain, or one cell inherit apical domain. So the cells which inherit apical domain, they start to flatten, they keep their polarization, and they start to form epithelium, which then becomes reticulaire. Whereas the inside apolar cells will then make inner cells, and then these inner cells, once the cavities start to be formed and push this group of inner cells one side of the embryo, become inner cell mass, and the first axis of the embryo is formed, embryonic axis. Now, the cells which flatten and start to form epithelium, they will express CDX2, start to upregulate CDX2 and GATA3, which are characteristic from markers for trophectoder, and the group of inner cells will start to upregulate markers for inner cells like GATA6, NANOT, and DOT4. Subsequently, these cells make another binary choice. Once some of the cells become this blue line here, primitive endoderm, and they will upregulate primitive endoderm markers, as mentioned here, GATA6, GATA17, GATA4, for example. And the other group of cells will upregulate pluripotency markers, like, for example, NANOT, or I will tell you a little bit more after about SOX2, which ensure that this group of cells remain undifferentiated plastic, and they can make all of the cells in our body. So, as I mentioned to you, by the time of implantation, all of the lineages are in an appropriate place, and they express appropriate set of transcription factors. So, trophectoderm here outside is expressing trophectoderm-specific factors like CDX2. Primitive endoderm, which is lining the cavity, is expressing primitive endoderm-specific GATA6 and GATA4, whereas the most inner group of cells, epiblast, is expressing pluripotency factors. So originally, it was believed that how the original specification occurs. Well, we thought it's simple. The cells which express CDX2 become trophectoderm, the cells which express NANOT become epiblast, and the cells which express, for example, GATA6 become primitive endoderm. But as often it is in real life, the biology is a bit more complicated than that. So, although by the time of implantation, what I told you is true, we have these three distinct lines, they all express distinct set of transcription factors. However, at the modular stage, so before the cavity is formed, all of the cells in the embryo will express markers for all of the three lineages, for trophectoderm, for epiblast, and primitive endoderm at the same time. How this is possible when later on it was reported that there will be inhibitory loop between these factors? Well, we don't know still. Nevertheless, once the outside layer of cells is formed, they will start, as I mentioned, to upregulate CDX2. So by the blastocyst stage, some of the cells outside will be expressing exclusively CDX2 in mouse, whereas the inside cells will downregulate CDX2 expression and will be expressing only GATA6 and or the primitive endoderm marker or epiblast markers, but still in this overlapping manner. And then gradually all of the outside cells will lose expression of epiblast and primitive endoderm markers, so they will only be having trophectoderm markers, whereas the cells inside also will decide, I'm becoming epiblast, so I'm red here, and I upregulate pluripotency factors and downregulate primitive endoderm factors, or vice versa, I become primitive endoderm, blue here, and I will downregulate pluripotency factors and upregulate primitive endoderm factors, and then the cells, originally they specified in seemingly random pattern, but maybe if you listen to some of the Sylvia's talk, you realize that probably it's not as random as we originally thought, but eventually they will specify to this nice spatially defined pattern. But as I mentioned to you, we still don't know how we get the red cells here. So I will tell you a little bit about it, how we try to understand it, and this is work of my PhD student who just finished. He was interested, what is the role of two pluripotency factors, KLF4 and SOX2, in the formation of epiblast? Why did we choose these factors? Well, according to at least some of the researchers, pluripotency network is established by having these two pluripotency core factors like OCT4 and SOX2, and based on the experiments with the embryonic stem cells, without these two factors, you cannot have pluripotency at all. So that's why they are core, named core pluripotency factors. But you also have these pluripotency supporting factors. So you can remove them from the equation, but only one at a time. And the cells still are pluripotent. However, the network is not very stable. And then you need some additional culture condition to keep the pluripotency stabilized. So they are important, but they are not absolutely crucial. So we decided to see what is the difference between them. Why OCT4 and SOX2 are core, and for example, KLF is the supporting one. So we chosen one core, one supporting, and we tried to understand what is the role in vivo. So there was quite a lot of work done on all of these factors in ESL settings, but in terms of the mouse work, not so much, although both mutant OCT4 and SOX2 were already done. But surprisingly, for example, the SOX2 mutant, the main phenotype was lack of primitive endoderm. So how do you reconsider that it's a pluripotency factor, but somehow affects mainly development of primitive endoderm? But this is actually due to the cell non-autonomous factors. And we decided, okay, but what SOX2 really does for pluripotency, and what KLF4 really does for pluripotency. We also chosen these two because those of you who are interested in regenerative medicine knows that both KLF4 and SOX2 are one of the 4 Yamanaka factors which can be used to reprogram somatic cells to pluripotency. So basically they have this very intimate link with the pluripotency, but we still don't understand how this is established during the development. So just to start from something, Ali originally made the staging for both KLF4 and SOX2 and to see whether they co-localize in the same cells and whether the pattern of the expression is similar. So as you can maybe see here, KLF4 is present, although on the various levels, in all of the embryos starting from 4th stage onwards, whereas the SOX2 distribution is a bit more complicated. So we can find it in the like 4 cell stage. We can find it in like 8 and 16 cell stage, although not very strong, but it's there. But if you take, for example, early 8 cell stage or early 16 cell stage, it's not there. So basically, SOX2 localization seems to depend on the cell cycle from some reasons. And there were various reports. Some researchers were saying that the SOX2 is present at these stages. Some researchers were saying that it's not. But if you think about it, that between these embryos and that embryos, there is 12 hours difference. It may be that one lab was collecting just early and the other one was collecting just late, and they come to completely opposite conclusion. So according to our data, I would say they are both right. It's just depending which moment of the cell cycle you look at. But it's also clear that these two transcription factors, pluripotency transcription factor, has a slightly different pattern. Then we go and look how it looks in the blastocyst stage. So SOX2, as was reported previously, is restricted just to the inside cells, whereas KLF4 can be both inside or outside cells, however it's a bit weaker in the outside cells, but it's still kind of everywhere. At the early blastocyst stage, again, SOX2 is present in all of the ICM cells, but only in ICM cells, when KLF4 can be still visible weakly, but still in trophectoderm cells. By the time when the process of lineage formation is initiated, we see that SOX2 is restricted only to epiblast cells. But KLF4, yes, it's upregulated in epiblast cells, but it's still present in the cells which will form primitive endoderm, just on the lower level. And finally, just after implantation, when we have a transition from what we call naive pluripotency, the most basic pluripotency, to the prime pluripotency, prime for differentiation, SOX2 is defining the position of the epiblast, whereas the KLF4, as you can see, is downregulated in both epiblast and primitive endoderm cells. Interestingly, it becomes upregulated in the cells which start to migrate, and this is just after implantation, another lineage will be formed, which is called parietal endoderm, and from again some unknown reasons, for the moment they will upregulate KLF4, they also will upregulate other pluripotency factors, and for the moment, yeah, I don't have an answer why they do it, but they seem to do it. But it clearly shows that although both of these factors at some point are co-expressed in the same cells, but the exact pattern of expression is different. Does it mean that they have a slightly different function? Perhaps. Now, how do we address this? What is their function? Well, as I told you, the data from the knockouts are a bit puzzling. And we thought, okay, we would like to distinguish the cell autonomous effects from non-cell autonomous effects. So what about just starts from looking at the cell autonomous effect of SOX2 and KLF4? In order to do it, we basically use the same trick which a lot of Drosophila people uses, or people who work on xenopus or zebrafish. We basically affected just a clone of cells within the wild-type embryo. So how do we do it? Ali is extremely gifted, so he can inject one blastomer at 8-cell stage with a different kind of RNAs. He was injecting either double-stranded RNA against SOX2 or KLF just to downregulate levels of these transcription factors, or he was injecting mRNA for these factors to upregulate the levels of these factors, but only in this clone of cells. He was injecting it together with a lineage marker, which here is H2B cherry. So basically nuclei of the injected first cells and then the progeny of injected cells are marked in red, so we can trace what the cells were doing during development. Of course, we have to confirm that our procedure is working. So here we have a control embryos, which were injected with double-stranded GP, which should be neutral for development, and our marker. And here we have embryos which were injected with double-stranded KLF4 and our markers. So as you can see, there's a mini clone of cells here. Basically, where the clone is, you hardly cannot see anything because the levels of KLF4 were very much downregulated. So you can see that the method works. Of course, if you upregulate it, you will have an opposite effect. We have two cells injected with mRNA for KLF4. You can see the difference in the KLF4 levels. And the SOX2, you barely can see it because it got so much upregulated that it's much, much stronger than the endogenous one, but anyhow, it's there. And then we cultured embryos for 48 hours, or actually Ali cultured embryos for 48 hours, and then he was looking at the distribution of the clones of the injected cells, which is clearly marked by the histone H2B cherry expression. We studied these embryos for GATA4 as our primitive endoderm marker and SOX2 as our epiblast marker to be able to assess to which lineages these cells contributed. And then we can see, for example, here, yellow cell, which has expression of GATA4. It means it contributed to primitive endoderm. Or, for example, these cells, which are negative for GATA4, but they are positive for SOX2. So it means that they contributed to epiblast. And finally, we have cells like these ones here, which are in trophectoderm, and they don't express neither CDX2, neither GATA4, neither SOX2. Therefore, they are contributing to trophectoderm. And here are the results of Alice's experiment. So when he was just injecting control, vast majority of the cells will contribute to trophectoderm. So basically to this line here, they are marked in blue. And this is normal because more majority of the cells at this stage in embryo is contributing to trophectoderm. After double-stranded CALF injection, even if we observe very strong downregulation of the protein, as you can see here, there is basically no any specific effect. However, if we downregulate SOX2, we basically completely remove this red line here, which is epiblast, and the cells contribute either to trophectoderm or to primitive endoderm, and we have a very small amount of cells which didn't express neither GATA4 neither SOX2, so they become this double negative cells, which maybe Sylvia at some point was telling you about. So they are the cells we just couldn't decide what they are. So from that we concluded that SOX2 is absolutely necessary to make epiblast lineage, whereas GATA4 seems too redundant for it. However, if you repeat the same experiment, but you inject double-stranded SOX2 and double-stranded CALF4 together, we will see that this potentiates the effect of downregulation of SOX2. And it pushes cells first mainly to the outside layer, and it gets rid of this undecided cells, and the cells can contribute only to trophectoderm, and small percentage can contribute to primitive endoderm, but they never contribute to epiblast, and they also are not undecided. So what will happen if we upregulate both factors? So again, we have our control. Majority of the cells again contribute to trophectoderm. If we inject CALF for mRNA, we do see that there is a shift. Less cells contribute to trophectoderm, more start to contribute to the inner cell mass, but the proportion of the epiblast and primitive endoderm cells doesn't change compared to the control ones. Yeah? Now, if we inject mRNA for SOX2, we have a much more drastic effect. So this effect is slight, but statistically significant, but as you can see, not as dramatic, by no means as dramatic as the overexpression of SOX2. So definitely, if you overexpress of SOX2, we give a chance to the cells much more to contribute to the epiblast. And this is on the expense of trophectoderm. So basically, what is happening, the cells are pushed inside of the embryo for some reason. Okay? But surprisingly, it does not change completely the contribution to the primitive endoderm. This cell still can contribute to the trophectoderm as much as the control cell. Why this is surprising? Because I hope you remember that I told you that there are binary choices. If there is a binary choice, why we didn't wipe out this population? Okay? Now, what will happen if we overexpress both SOX2 and CALF4? Then we are able to completely almost get rid of primitive endoderm. And of course, again, we have a dramatic increase of the cells contributing to epiblast. So, although as I told you, so far, majority of the consensus in the field is that there is a binary choice, but our data seems to suggest that there are two mechanisms. One is based on upregulation of pluripotency factors like SOX2, and the other one is somehow related to the presence of both SOX2 and CALF4, which basically only then can reduce number of primitive endoderm cells. So what I told you in this part is that we have definitely very strong influence of SOX2. SOX2 is definitely necessary to make pluripotent cell line, but it's not enough to basically turn all of the cells to epiblast, and you need the CALF4 contribution to somehow suppress differentiation towards primitive endoderm, and at the same time, the cells have to upregulate SOX2. Because if you just have a KLF suppressing, at least partially, primitive endoderm, it's not enough to make the cells into the epiblast. Now, I would like to change the subject, if you don't mind, a little bit, because this is mouse, which is, I still believe, very important to work on it, but what happens in other mammals? We know more and more that human embryos bovine embryos seems to be slightly different than mouse embryos. So, together with my long-time collaboration, Anya Kilishek, we start to look for another model organism for mammalian development, which we would like them to be a bit like mouse. So we can have a lot of embryos. You can collect embryos not from the in vitro culture, not like human embryos or bovine embryos, but we want to collect them freshly from the mother and preferably without hormonal stimulation, because it is believed that all of these factors can influence development. So where do we look for embryos like this? Well, we found an animal actually, which breeds like rabbit, so it means has a lot of embryos, and this is a rabbit embryo. They go through similar stages, like all of the mammals, they divide. Cells are getting smaller and smaller, but you can still clearly see them. They divide to 4, they divide to 8 cell stage, and they will divide to 16 cell stage, as you can see. But what is interesting, we still see the difference between the cells. We can still see where the cell is. So basically, rabbit embryos undergo compaction later than mouse embryos, either at late 16 cell stage or early 32 cell stage, which is exactly like a human embryos in the, of course, perfect condition. Then, of course, they will keep developing further, and eventually they will form a cavity, but the way they form a cavity is very different than the mouse, and I will come back to it later. They just make this kind of ring, and then the ICM makes this kind of round structure in the middle, and only then it becomes flattened at one side, and then embryo starts to hatch. What is interesting, when I show these movies to people who work with the human embryos, they will say, "Oh, they look exactly like a human embryos," and this is true. They have a lot of difference with the mouse. So although they go through the general same stages, but they have additional stages which mouse don't seem to have. So, okay, you can say, well, they start everything later because they just develop slower and that's it. Well, actually, that's not true. So, in mouse, and often in other animals as well, we count the development from the moment of fertilization. And we call it embryonic day, E. For example, 0.5 means that this stage is 12 hours after fertilization, and then you have day 1, day 2, or day 2.5. And so on and so on, and we can see the development. Well, actually, rabbits develop faster than mouse, believe it or not. So when the mouse is dividing to 2 cell stage after sometimes even 28 hours, the rabbit is already 4 cell stage. Then when mouse divides to 4 cell stage, rabbit is already 16 cell stage or more moruli, because rabbit embryos divide every 6 hours. When mouse is just making moruli, they already start making blastocysts, and then they go to the stage which mouse doesn't seem to have. This is a kind of round ICM, which again, I will show you later. The pictures is characteristic for many other mammals, but mouse does not have this stage. Eventually, they will stretch in a similar way as mouse does, and then, but at the end, they become almost completely flattened. Again, in a way much more similar to human embryos, whereas mouse post-implantation will start to make this kind of cylinder shape of the embryo, which other non-rodent mammals don't have it. So because we seem to have more stages for rabbit than for mouse, we had to develop additional staging system. So in mouse we usually count cells, as again you can probably see from Sylvia's experiment. But in addition, just to avoid confusion, we start to call them stage 5, stage 6. It basically means 5 divisions after fertilization, 6 divisions after fertilization, 7, etc. But basically, for example, stage 7 is the stage when we have this kind of very round ICM sticking out into the cavity, and only later on become flatter, and at the end you have almost completely flat disc. Now, what is interesting also, rabbit embryos start gastrulation just before they implant. So that was at some point a lot of argument whether the gastrulation is induced by the contact with maternal tissues. Well, rabbit tells us that is not necessary, because they can start doing it without any contact with maternal tissue, and in fact, in vivo, that's what they do. Here, for example, we have an OCT4. This is day 4 of development. So remember, in mouse, it's already pretty advanced, but in rabbit it's even more advanced than in mouse. And we see OCT4 both in ICM, stronger expression here, but we also see in trophectoderm. And one can say, okay, maybe it will never become non-related. Well, it will eventually at day 5, almost when the rabbit embryo prepares for gastrulation. So it means that OCT4 is in trophectoderm for much longer than in mouse. And similarly, if you look at the CDX2 expression, you remember I was telling you that in mouse the expression starts already at 8 cell stage and then just become upregulated in outside cells. Whereas rabbit, you can form perfectly fine blastocysts. Like this is a 3D of blastocysts, view of blastocysts. Here we have ICM, here we have a cavity, and as you can see, there is only a few cells which are positive for CDX2. And in rabbit, you can easily find the blastocysts, which will have not a single CDX2 positive cell at this early stage. Eventually, of course, you will have upregulation of the CDX2 in trophectoderm, but as you can, for example, look here, there will be still some cells in the trophectoderm which don't have any CDX2 expression. And there was this disagreement between several groups in our field, which some groups were claiming that we need a CDX2 for blastocyst formation, some of the groups were saying that we don't, but as you can see, rabbits and actually humans can do it easily without it. So if you look at the human embryos and CDX2 expression, that's the data from not from my group but from other groups. But you can see clearly that originally there is almost no CDX2 expression, and even at the day 6 of development there will be some cells which, exactly the same as in rabbit, don't have any CDX2 expression yet. And similarly, OCT4 will be kind of everywhere originally. Later on, it's stronger in the ICM, but the trophectoderm still has a OCT4 expression. So originally, when this work was published, a lot of people was saying, oh yeah, but you know, they are in vitro culture embryos, they are after hormonal stimulation, and they are from the in vitro phase. Probably they are not normal, and that's why they look like they look. But the rabbit embryos, which I just showed you, look exactly the same. Even if there was no hormonal stimulation, because in rabbit you can induce ovulation by just mating the rabbits. And there was no in vitro culture, we just freshly flushed them from the mother, and we end up with exactly the same result as the human embryos. Now, again, this is the human embryos from Jenny Nichols' lab. If you look at the primitive endoderm markers like GATA6, again, it's everywhere, as OCT4 in human embryos. And if you look at the rabbit embryos, you can see that again, it's exactly the same. GATA6 is everywhere, and you cannot even say that it's stronger in ICM, because it's not. And by the way, this kind of nice round circle which you see here is because this is the state where we have this nice kind of round ICM sticking inside of the cavity. So, in general, rabbit embryos seems to be much more similar to what we observe in the human embryos and also other species than in rodents. Okay, but I don't know if you noticed, but we have a problem here. If GATA6 is expressed everywhere, basically, we cannot really use it as a reliable marker of primitive endoderm. And actually, it's the same for nanite. Nanite is everywhere at this stage as well. So to work with rabbit embryos, we had to develop some other markers, or at least find some other markers which would be more specific. And just to cut a long story short, we try a lot of different markers, but finally we figured out that SOX2 actually is pretty good indeed marker of pluripotency, and it's much more specific than any other marker we checked. And it will be expressed in rabbit only at blastocyst stage. Our marker from primitive endoderm, we decided to use SOX17 because, again, this expression is very specific, only in few cells. However, when the expression initiates, some of the cells will upregulate SOX2 and some of the cells will upregulate SOX17 at the same time. So again, it looks like these two decisions, to be epiblast and to be primitive endoderm, are not completely dependent, at least at the beginning. But eventually, as in mouse, everything will sort to the right place. SOX2 will be only in epiblast, and SOX17 will be in primitive endoderm. However, in rabbit, it looks slightly different. It kind of makes this kind of ring, because remember, it's a flat, almost completely flat structure by this stage, and actually reminds a chicken at this stage. much more. Okay, but now we wanted to understand how these two lineages, primitive endoderm and epiblast, are formed in other than mouse species. So, but to tell you the story, I have to go back to mouse for a second. So in mouse, I told you that we have this originally overlapping expression. However, if we treat normally for 48 hours with excess of FGF4, we can turn all of the cells in the ICM towards primitive endoderm. And vice versa. If we block completely FGF signaling for 48 hours, all of the cells in mouse in the ICM become epiblast. Okay? Now, very similar experiment were repeated in humans. They basically took the human embryos, blocked the FGF for 48 hours, but the result was different. So basically, in humans, you cannot transform all of the cells in the ICM towards epiblast just by blocking FGF pathway, and that was done by several labs by now. So there seems to be a difference, again, between rodents and other mammals. So we try to understand what will happen if we repeat the same experiment, but in rabbit. Okay, so this is our control embryos. You see, if you just culture a rabbit embryos, they will eventually differentiate to the epiblast, here markers of the expression in green, and primitive endoderm in magenta, marked by SOX17 expression. If we give them access to FGF4, exogenous FGF4, almost all, and in some members all of the cells become SOX17 positive, with very few SOX2 cells left, and in some members, as I said, there will be no single SOX2 positive cell. So that looks very much like a mouse. If we block ERK, we have a formation of SOX2 positive only cells, and there will be no SOX17 positive cells, which looks originally very close to the mouse. But look at this data. We actually count the number of cells. So in the control embryos, we have a similar situation like in mouse. We have our magenta primitive endoderm cells, our green cells, epiblast cells. We have a double positive cells, which can be observed in mouse. We have double negative cells, which again, they also can be found in mouse. When we treat embryos with FGF4, almost all of the cells become magenta primitive endoderm, with very few SOX2 positive cells left. But if we block ERK, yes, we do have epiblast, but look, the percentage of epiblast cells didn't change between these two conditions. All of the remaining cells are, yes, they are negative for SOX17, but they don't express pluripotency factors. So again, it looks like blocking FGF in mouse is enough to turn them all towards epiblast, but not in other species. And if the cells don't get additional signals, they seem to just be lost and they don't get any identity. So in mouse, we still have this model. If we believe it, that we have the binary decision, high levels of FGF signaling gives us primitive endoderm, low levels of FGF signaling give us epiblast. But in rabbit, if you have high levels of FGF, yes, you make primitive endoderm, but low levels of FGF does not make anything in particular. So how to make epiblast in rabbit? Well, we do know that we need low level of FGF, but we definitely need something else, and for the moment I can all tell you it's our factor X, because we don't know what it is exactly, to make epiblast. So this decision seems to be not as binary as it seems, but as you could see from the first part of my talk, probably in mouse even, the decision is not as binary as we thought. Now, let me go back to this strange structure of this kind of round ICM, which we can observe in bovine embryos, in human embryos, in rabbit embryos, but mouse doesn't have it. And I will just prove it to you that the mouse doesn't have it at any moment. It's not like short transient state or anything like that. So here you have a movie made by my first PhD student, actually. This will be a bit slower formation of the blastocyst, just to show you that once ICM is formed, you see, there is no single moment when you have this round ICM. Yeah? I'll play it just in case again. Okay? So we have a modular formation, and soon we'll have a blastocyst formation, but there will be not a single moment when we have this structure. Yeah? You can see here. Whereas if you look at the human embryos movies or rabbit embryos movies or any other, actually, this stage is always there. But does it matter? Well, actually, we think it does, because there is a reason why here you don't have this stage. The possible reason is that adhesion in mouse embryos is much stronger than in any other mammals, for whatever reason. Now, I told you about the experiment in which we are treating our rabbit embryos with FGF. So, all of the cells turn into the SOC17 positive cells, here in magenta again, but they didn't look exactly the same as a control. In control embryos, all of the cells were where the ICM was, or they dispersed a little bit, like some of the cells left the ICM. Whereas in our FGF-treated embryos, we didn't have this type of cells, this type of embryos at all. Almost all of the embryos, the cells migrated either like at least halfway through, or they populated the whole cavity, and they basically could just see them all over the place. So what does it mean? It probably means that in mouse, when you have a strong adhesion, the cells are kind of prevented from migrating far away, whereas in other species, when there is not such a strong cell adhesion, the cells cannot be stopped from migrating, and they go all over the place. But does it mean that FGF has a different function in mouse than other species? Well, actually not necessarily. So again, Nestor made an experiment in which he cultured embryos from morula stage to blastocyst, but for 74 hours, not 48. And in fact, he could repeat the same phenotype with mouse embryos, not exactly the same, but similar. So indeed, the cells mouse embryos, which are cultured with excess of FGF4, the primitive endoderm cells also will start to migrate, and they will lose basically ICM, and we will have this just strange structure with just two layers of cells present. But it will take them much longer, probably because the migration is suppressed. So, to summarize what I just told you, mouse and rabbit, they go through the similar stages. All of the species tested so far seems to have this overlapping expression originally, and it's not artifact of the culture because freshly cast embryos show exactly the same pattern, which will be gradually restricted to the only particular cell type, and then also originally the cells will be scattered within the ICM vertibrosis primitive precursors, and only later on they will sort themselves. So this is similar. However, it does not happen at the same stage. In other species than mouse, it will happen during a different cell cycle. However, each species seems to have this very tightly regulated. In mouse, the cell specification event in an ICM will always start at 64 cell stage, whereas in a rabbit it will be during the transition from stage 7 to stage 8. And they are very clearly defined lines, although they don't have to be the same for each species. But we will have many differences coming, for example, not necessarily from the different genetical cycles, but because the embryos has a bit different geometry and a bit different cell-cell interaction. So, what I just told you from this part is, as I said, the mammalian embryos share equivalent stages, although timing can be different and architecture is different. Therefore, some of the things which we observe will just look different just because of that. And although FGFR plays an important role in lineage commitment in rabbit, but it does not exactly mimic what happens in mouse. Do I say now that we should stop working on mouse and work on something else? No, by no means I don't want to say that. I just want to say that we cannot study only mouse and then assume that what we know from mouse will be true for all of the mammals, and we need more model animals, and I would strongly recommend rabbit. But of course, we can work on other animals in order to understand properly mammalian development. And now I would like to thank my collaborators and the people from my lab whose work I presented. The first part was done by Alia Mbaki, and I showed you a little bit of experiment of the Nestor Sais, and the whole almost rabbit part was done by my collaborator Anna Pilishek with a bit of the help of Ania Stachowiak and Zofia Madea. And as you can see, all of what I presented to you is definitely international collaboration. We had some funding from the Polish funding bodies, British, Spanish, and Iraqi. So I would also strongly suggest that we try to make as many collaborative things between the countries as we can, because as you can see, we can have a very nice story. Thank you very much for listening.